Yeah, sorry. Can wait a few minutes? Sorry, I have to use my another.
Oh, I see.
Yeah, I have some. Sorry, I have some problem with the share screen. So let me use my another laptop.
Yeah, it's okay.
It's okay now?
See it. Yeah.
Okay. Yeah. Sorry. Yeah. Sorry for the technical problem. Yeah. Yeah. Okay.
Yes, it's okay. Yeah. So let us start the morning session of the second day in our workshop. And our first speaker is Professor Ki Lee from SUSTech, and the title is Holomorphic Differential Operators by Fields of Quantization. So please start.
Okay, thank you very much for the introduction, and also thank the organizers for the invitation to this joint workshop. The title of my talk today is Holomorphic Differential Operators via Fields of Quantization. Let me start from some introduction of the motivation, which I will explain more in later sections. So the main motivation is to quantize. So I'm working on deformation quantization and geometric quantization. So the main motivation is to quantize a subclass of smooth functions on a Kähler manifold to differential operators on certain holomorphic vector bundles. This has the following advantages comparing to the well-known Berzin-Topliss quantization. And actually, I will say also later the Fields of quantization. So first of all, this gives rise to a non-formal deformation of the classical pointwise multiplication of functions. And the second one is, so in Berzin-Topliss quantization, usually people will talk about the Hilbert space as the holomorphic sections of the so-called pre-quantum line bundle. But in our program, this construction is not limited to pre-quantum line bundle, but to general holomorphic vector bundles. And the third is functions, smooth functions are quantized to operators, which are local instead of the asymptotic locality in Berzin-Topliss quantization, which I will say a little bit later. So this is what physicists would prefer. That's the locality. So the background or the geometric background is about deformation quantization. So this is a mathematical description of observables in a quantum mechanical system. More precisely, we know that on symplectic manifolds, or physically the phase space for classical mechanical system, we have the Poisson algebra of classical observables. And in deformation quantization, these classical observables is deformed to an associative algebra of quantum observables. So in general, these are not commutative anymore. And also, this also fits the so-called canonical quantization on the mathematical side. And so let me give you the definition here. So the let M and omega be a symplectic manifold. Here, omega denotes the symplectic form. Then a deformation quantization of M is an associative product on this space of formal functions. So H bar here is a formal variable such that F star G, so that's the star product, that equals F times G, which is the leading term, and the classical part, by classical, I mean there's no H bar, and plus the infinite sum of H bar to the i's power times Ci of Fg. So here, Ci's are bidifferential operators. So in fact, they are local. With the first term is C1Fg minus C1GF equals the Poisson bracket between F and G. So that is saying the Poisson bracket is the first order of non-commutativity in this picture. So these requirements for deformation quantization actually comes from the so-called Dirac axioms, although it's not satisfied. I mean, all the items of the Dirac Dirac axioms are not satisfied, but we have to find some compromise. So this is the mathematical description. So there are actually two known schemes for quantization or the construction of deformation quantization. One is the so-called Fedosov quantization, which is more algebraic. And there is also the Berzin-Topliss quantization, which is more of an analytic flavor. So let me start from Fedosov quantization. So Fedosov's idea is very simple. So he actually gave a very geometric construction of deformation quantization on a symplectic manifold. So what he did is he considered the so-called Weil bundle. So this is the completed symmetric product of the cotangent bundle on a symplectic manifold. So on this infinite rank bundle, there is an associative but non-commutative product, fiberwise product, which is called the Moya product, or some people call that Moya-Weil product. And he shows the following theorem, which is basically his the detail, which is basically the idea of his construction. So the first thing is he constructed, or he showed the existence of a flat connection, which we call D, on the Weil bundle. Now it is called the Fedosov connection. This connection is compatible with the fiberwise Moya product. In other words, this is a connection which is actually a derivation with respect to this fiberwise Moya product. And there is the following isomorphism between formal smooth functions and flat sections of the Weil bundle with respect to the connection D. So that is smooth formal functions is actually canonically isomorphic to flat sections of the Weil bundle. And this isomorphism is explicitly given by taking the so-called symbol, because Weil bundle, as we just said, it's a formal completed symmetric product. And if you take the leading term, meaning that you take the what we call the scalar part, and you get the function. And the fiberwise Moya product on the flat sections actually gives you a deformation quantization, because we have the compatibility condition. Say D is compatible with the Moya product, meaning that if you take a star product of two flat sections, then you still get a flat section. And that's how you get a deformation quantization in this Fedosov construction. And another known construction is the so-called Berzin-Topliss quantization. So these are defined via the so-called Topliss operators on pre-quantizable Kähler manifold. So this is defined as follows. So first you pick a
Excuse me, sorry.
Yeah.
May I ask a question?
Yeah, sure.
Oh, originally, in the formulation of deformation calculation, manifold is assumed to be just a symplectic manifold.
Yes.
In the following,
Yes.
do you assume it is also Kähler? Do you need complex structure?
Well, for the general Fedosov construction, you don't need it to be Kähler. You just need a symplectic manifold.
Yeah,
That's
yeah.
enough. Yes.
But in the following, you assume it is also complex. Sorry, Kähler manifold.
Yes. So
Why do you need?
Yeah. So what I'm doing is I only work on Kähler manifolds.
Mm-hmm. But
Yeah.
why? The reason? Do you need some complex structure?
Yeah, I will say, actually, I will explain later that. So Fedosov's original construction, so that only requires symplectic structure. But what we found is that when there is Kähler structure, you can actually find very special Fedosov connections.
Mm-hmm.
So that requires the complex structure. So that's the reason I only restrict I mean, in my program, I only restrict to Kähler manifolds.
Okay, thank you.
Yeah. So the Topliss operators are defined on pre-quantizable Kähler manifold. So first you pick a pre-quantum line bundle L on M, which requires that the first chunk class of L is actually equal to the symplectic form. Of course, there are certain, you have to normalize that. And so you cannot, you can take in general, not only the pre-quantum line bundle, but actually you can take its positive tensor powers. So you can take L to the tensor power K, and then you can construct the so-called Topliss operators. So given any smooth function, the Topliss operator associated to this function f is defined as what we call multiply and then project. So it's defined as TF, that's equal to first you multiply a holomorphic section of L to the tensor power K by this function f. And because f is in general only a smooth function, so in order to get a holomorphic section of L to the tensor power K, you will need to do a projection. Of course, here you can do the projection because you have this mission inner product, and then you have inner products on these sections of this line bundle, and then you can do the projection. And the main result is actually if you take the composition, so in general, the composition of two Topliss operators is in general not a Topliss operator anymore, but you can look at its asymptotic behavior as K goes to infinity. And the asymptotic formula of the composition of two Topliss operators actually induce a deformation quantization. Now, so from the, we can, if we look back to the definition of deformation quantizations, say if we look back here, so we require these CIs are bidifferential operators. In other words, they satisfy locality. So that is saying the Brazilian Topliss quantization is actually not, their composition is not asymptotic. Sorry, it's not local, but only asymptotically local as K goes to infinity. So I can give here a very specific example. That's the so-called Fock space, or some people call that Bachmann-Fock space. So the Fock space is, so that's the simplest example. So you look at Cn, right? That's the simplest complex Kähler manifold. So you can look at holomorphic functions because every line bundle here is actually trivial. So you can take, you can look at holomorphic functions, and then you look at a volume, which is essentially the Gaussian, which essentially gives you the Gaussian measure. And here H bar is any positive number instead of a formal variable. And there is the so-called Bachmann-Fock representation of the weak algebra. So here we restrict ourselves to some simple functions, say polynomials. And we can look at the Topliss operators associated to these functions. So as we said, the construction of these Brazilian Topliss operators is defined as multiply and then project. So we can look at some simple examples. For instance, you can look, we can set it to be the simplest case, say n equals 1. So that's on C. And you look at Topliss operator associated to this function Z. And that's nothing because Z is already holomorphic. So you don't need to do projection anymore. So that's just the multiplication by Z. And also you can look at TZ bar. And it turns out it acts as a differential operator. So that's H bar dZ. And if you look at something more complicated, say polynomials, so you can split them as holomorphic polynomials and anti-holomorphic polynomials. For instance, it's z bar to the m, z to the m. And it turns out that you get the so-called weak ordering. So that means you first multiply those holomorphic things, and then you let these z bar m's act as differential operators. So this is these are the Topliss operators on the flat space C. Of course, it works on general Cn. And turns out you can make it an algebra that's called the weak algebra, and the product is also called the weak product. And you can make this very algebraic. For instance, you take this f star g, and you have this explicit formula. And I should say that this is actually a polarized version. So this is a weak product. So that's a polarized version of the Moya product in symplectic geometry. And here we can actually take not only polynomials, we can take formal power series. So these are, this is the explicit example of Brazilian Topliss operator. So that's on the simplest Kähler manifolds, say flat spaces. And we can also make this action. I mean, we can also make this Hilbert space more algebraic. So that's the so-called Bachmann-Fock space, which consists of only holomorphic functions. So the action is pretty simple. So holomorphic things act on this FCN as multiplication, and anti-holomorphic things, say Z bar, acts on these this space as a differential operator. So that's this example here. So I have said two constructions of deformation quantization. Although these are very well-known construction of deformation quantization, so there are still some drawbacks of these quantization schemes, which is actually the main motivation for this work. So first of all, is in both Fedosov and Topliss quantization, what we get is a formal deformation of smooth functions. So that's where the reason we have to allow these formal variable h bar here. So for the Fedosov quantization approach, there is no Hilbert space. So you only see this star products, this algebra, associative algebra of star products, but there is no Hilbert space where it should act on, and that's the that should be the whole complete picture of the quantization. And for Topliss quantization, there is also a drawback. That is, although we have Hilbert spaces, so mathematically it's constructed as the holomorphic sections of L tensor power k. And you can see, the idea here is that Hilbert spaces is where these operators should act on. So mathematically, we can say that this Hilbert space should form a representation of the star product. But this is only true in the asymptotic sense. In other words, this is only a representation of the deformation quantization as k goes to infinity. So these are some drawbacks of these constructions. So what we did is we tried to apply the Fedosov quantization construction, and we can overcome these drawbacks. So any questions?
Oh, is there any physical meaning of K?
Yeah, so later actually we can see that that's what we call the level structure. So actually this is also in the Chern-Simons theory picture.
It's a kind of quantization parameter?
Yeah, it's a quantization parameter. So
So it looks like some classical k goes to infinity looks like a classical limit. Is it correct?
Yes.
No.
K goes to infinity. That's a classical limit.
Yeah.
It. Yes. So
Okay.
K is playing the role of 1 over h bar.
Well, yeah. Yes. Okay.
Yeah. So that's a simple way of saying that. Okay. So the first thing is we want to get some non-formal quantization. So we should we want to get rid of this h bar here. So so there is actually a very simple observation. So in the case of polynomials on Cn, we can actually evaluate h bar at any complex number. So we don't need to worry about the convergence issue, and we don't have to take the formal variable. And so a natural question is, so can we generalize these polynomials to Kähler manifolds? So so that we can get some non-formal quantization of functions. Of course, there are certain payoffs, and we will see that the payoff is you have to restrict to a subclass of smooth functions. Just like in Cn, you have to restrict to polynomials, or at most some power series which have certain convergence properties. But anyway, so the point is, can you find this subclass of functions? And okay, so this is actually related to the first question. So why is Kähler structure so? Why do we need Kähler structure? It turns out that what we find is actually a class of Fedosov connections. So that arises from the so-called L-infinity structure on Kähler manifolds. And this actually gives us, this can be a tool for constructing these polynomial functions. So let me give a very brief recall of this L-infinity structure, which is introduced by Kaplanov I think in 1996 for his in the construction of so-called Rosenski-Witten invariants. So the L-infinity structure on a Kähler manifold X is actually equivalent to a flat connection. So or more precise, we can reformulate it to a flat connection on the so-called holomorphic Weil bundle. So it's not the standard real Weil bundle, but the holomorphic ones. So in other words, it's a complex symmetric product of the holomorphic cotangent bundle. And this connection we call dk. So k is for Kaplanov. So that is of the following form. So that's nabla minus delta plus a bunch of operators. So these operators are in tilde star are defined as partial transpose of covariant derivatives of the curvature tensor of the connection. So this is a little bit complicated. The reason this is called L-infinity structure is it's actually a generalization of the standard Lie algebra structure. So that's the structure first. Well, so this L-infinity structure on Kähler manifolds is first brought up by Kaplanov. So this is something totally classical. So there's no H bar in this game, and if you look at the flat sections associated to this connection, it's actually isomorphic to holomorphic functions. So of course, if X is compact Kähler, you have to look at local holomorphic functions. And the interesting thing is we can actually quantize this L-infinity structure. So what we did is we actually consider the complexification. So we take not only the holomorphic Weil bundle, so we take the complexified Weil bundle. So that means we not only have a complete symmetric product of holomorphic cotangent bundle, but also a completely symmetric product of anti-holomorphic cotangent bundle. And so let me skip some details here. So what I mean, a quantization of this L infinity structure is that what we can find is a Fedosov connection on this complexified wire bond. And it's of the following form. So we call this DF. So F is for Fedosov. So you can see that it looks quite similar to DK. So there is this Levi-Civita connection here, minus this delta operator, plus a certain bracket. So in other words, we have replaced these, so let me, here. So we have replaced this bunch of Rn tilde stars to these brackets, In. So this is the bracket associated to the fiber-wise weak product. And the reason we call this a quantization of the L infinity structure, or more precisely, a quantum extension of the L infinity structure is the following. So if we restrict this Fedosov connection to the holomorphic part, I mean the holomorphic wire bundle part, right? Because the complexified part, complexified wire bundle is the tensor product of this Wx and Wx bar. So if we restrict to the holomorphic part, then we actually recover the flat connection in Kapranov's L infinity structure. So that's the reason we call it a quantization or quantum extension of the L infinity structure. And the first good thing about this construction is, so we know from general theory of Fedosov construction. So once you have a Fedosov connection, DF here, then we will have a one-to-one correspondence between smooth functions and flat sections of this DF. So that's the first thing. And more importantly is that because our Fedosov connection is obtained from the quantization of this L infinity structure, it actually satisfies very nice properties. So first of all, it turns out that this is only a polynomial in H bar, not a formal variable anymore. And actually, we actually have that this is at most degree 1 in the power expansion of H bar. And that actually means, because this is only a polynomial in H bar, so that means we can actually take evaluation of this H bar at any non-zero complex number. So we can take H bar to be 1 over K. And in this way, we can define a subclass of functions. So the first thing is, in the definition, so a smooth function, we call that a quantizable function of level K if there exists a section of the wire bundle such that the following 3 conditions are satisfied. The first one is the symbol of this flat section is F. And second is this section, of course, we need this to be flat under this connection dk. So that is dh bar evaluated at 1 over k. So this, you can only do this on Kähler manifolds using this Fedosov connection, but not the original construction of Fedosov. And third is we actually have a finiteness condition. That is, in this flat section, we require a uniform bound in the anti-holomorphic degree of the wire bundle. So in other words, so this Kc is a section of Wx tensor with Wx bar. So here we have this subscript less than or equal to n. Of course, on this wire bundle, we can talk about polynomial degree. So in other words, we require this section has a uniform bound on this anti-holomorphic polynomial degree. And so the third condition is actually exactly the polynomial condition we want to generalize from the flat space CN. And a natural question is, of course, you have Fedosov connection, and you can talk about flat sections. But are there examples of these functions we have just defined? In particular, the third condition, right? Because you wanted to have a polynomial degree condition. And actually, there are many examples. So let me say two. So the two main examples is, so first of all is, so on Kähler manifolds, you can take the so-called Kähler potential. Of course, they only exist, they are well defined locally, you can find them. And if you take the holomorphic derivatives of these Kähler potentials, and these functions are actually these quantizable functions we just defined. So these are the first examples. And these examples tells us that actually locally there are enough such functions. And second class of examples actually comes from symmetries. So that these examples are called quantum mode maps of Hamiltonian symmetries on Kähler manifolds, which actually preserve complex structure. So the second class of examples is also interesting because it's related to symmetries, and also they actually give you global quantizable functions we just defined. So for instance, you can look at something, some interesting Kähler manifolds, for instance, cojoint orbits, which are related to representation theory. And actually it tells you that these functions actually are dense on these cojoint orbits. So anyway, so these examples tells you that this definition is not empty. So we have plenty of examples of these functions. So why are these functions important? Is that actually we can quantize them to differential operators. So we actually define the so-called Bachmann-Fock sheaf. I can say a little bit motivation behind this. So the original Fedosov construction is how you can define a star product, quantum product for algebras. And so these Bachmann-Fock sheaves is an extension of Fedosov's construction for modules. So first, the Kähler form on X actually enables us to define the fiberwise Bachmann-Fock action. So making the holomorphic wire bundle actually a sheaf of WXC modules. These are nothing but the generalization of the local picture on Cn. So explicitly a monomial X as an operator on Wx as follows. So you can see that this is this actually comes from the computation on Cn. So these holomorphic ones Yj bars X as differential operators, and these holomorphic ones, say Yi1, these act as multiplication one operators. So this is how we can define the fiberwise Bachmann-Fock action. And it turns out we can make these fiberwise things global. Again, we can define some Fedosov connection. So what it turns out that to construct a flat connection, which we also call that a Fedosov connection, we need to twist the holomorphic wire bundle by the pre-quantum line bundle, or in general, its tensor power, depending on the level K here. So that is defined as what we call FL tensor K. So that's the holomorphic wire bundle tensor with L to the tensor power of K. And we can actually construct a theorem so I can construct a connection on the level K Bachmann-Fock sheaf. And important thing is first, it's compatible with the Bachmann-Fock action, and it's also compatible with the Fedosov connection on the Weyl algebra part. So in other words, we have Weyl algebra, we have Bachmann-Fock module, and on both sides we have flat connections, and actually they are compatible. And the first thing is, so if you look at flat sections of this Bachmann-Fock module sheaf under this connection, it's actually isomorphic to holomorphic sections of L to the tensor power of K. So this actually gives a sheaf theoretical interpretation of the Brazilian topless quantization. So why you need to take holomorphic sections of L to the tensor power K, and this actually gives a sheaf theoretic explanation. And it turns out that, so if we look at, so quantizable functions, which we denote by this curly C infinity, and we also have a subscript K here, which denotes the level. And it turns out these quantizable functions is actually isomorphic. There is actually a canonical isomorphism from this quantizable functions to holomorphic differential operators on this pre-quantum line bundle and its tensor power, depending on the level K. So this actually tells you that we can find an explicit subclass of smooth functions which are quantized to not only topless operators, but actually they quantize to differential operators. So in other words, they satisfy the good properties we want. First, it's non-formal, meaning that we can take the value of K, of level K. So it's non-formal. And second is it satisfies the locality because it's a differential operator. And actually this isomorphism is actually, there is, of course, on the right-hand side, for differential operator side, we have a filtration by the degree of differential operators. And on the left-hand side, there is also a filtration defined by the degree of anti-holomorphic parts, anti-holomorphic components of the Weyl bundle. And it turns out that these two filtrations are compatible with respect to this isomorphism. And this actually gives us how we, this actually shows our quantizable function can be actually quantized to differential operators via this generalized Fedosov construction. Yeah, okay, so I will just stop here.
Thank you for the very interesting talk. Is there any comments or questions? No. Let me ask.
Yanai-san, okay.
Hi.
You want to ask? May I ask a question? Yeah.
Yeah, sure.
Yes, please.
Yeah. If I remember correctly, in connection with L infinity algebra, there's some work by Maxim Kontsevich on deformation quantization. Do you know?
Yeah. Yes, yes.
Can you tell us the relation to his work and your talk?
I think it's a different thing because Kontsevich, what Kontsevich did is in the geometric context of Poisson manifolds.
Yeah.
So that's like weaker than symplectic manifolds. So what I did here is actually stronger. The geometric condition is actually stronger than the symplectic manifolds because we require Kähler.
Yeah, that is related to my first question. So you are working on Kähler case, but Kontsevich work is on general symplectic manifold. Is it right?
Yes, it's his work is on general Poisson manifolds. It's more general, yes. Yeah.
And another question is, on L infinity structure, there is some categorical interpretation. Is it right?
Which condition? You say again?
Yeah, on L infinity algebra structure, I thought it allows some categorical interpretation. Is it right or no?
Sorry. Can you just say again?
No. Maybe I'm wrong. Yeah, if I remember correctly, the infinity structure is related to some modular space of Riemann algebraic curve or Riemann surface, and in that sense, it is related to some categorical. It allows some categorical interpretation. Is it right, or am I wrong?
Yeah, I think there are actually. I think there are some categorical interpretation, but here we are not using that. We are just using the very explicit L infinity structure here.
I see. Thank you.
So let me ask one question. So if we change or deform the Kähler structure, then what happens?
Yeah, so that's a very interesting question. So one project I'm working on, so it's not, so I'm trying to deform the complex structure, but keeping the simplex structure. And in that case, there is the notion of so-called hitching connection. And in that, so what I'm working on is trying to relate this hitching connection to Fedosov connections in families. Because if you form these things, then you have a parameter space for your deformation, and then you can try to extend these Fedosov connections to families by allowing the Ram differential on this parameter space to come in. And you want to see if there is a flat section in that case. And so what I'm trying to prove is that, so the flatness of Fedosov connections in families is actually equivalent to hitching connection.
Yeah, it sounds very interesting. Yes.
Yeah.
Thank you. And is there any other questions or comments? Then let us thank the speaker.
Hey, thank you.
Thank you very much. So the next speaker is Jinli. So please take session chair.
Okay. So when should we start? Sorry for the technical problem I had.
You can choose.
So how about we start in 5 minutes or?
Maybe we can start from 25.
25, okay.
25.
Okay.
I think it is better to prepare next speaker because there is some risk for trouble. So it is better to prepare next speaker now.
Now?
So next speaker should prepare or at least share the screen now. So Yamaguchi-san, so
okay.
please
Ah,
share your slide now.
okay. Okay.
Okay, okay, thank you very much.
Okay, welcome back. So the next speaker of this morning's session is Professor Kohei Yamaguchi. So the title of his talk is McDonough conwinder polynomial as multivariate Q orthogonal functions.
Thank you for the introduction. I'm Kohei Yamaguchi at Nagoya University. I would like to thank the organizer for giving me the opportunity to give a talk. I will talk now. This talk is an introduction of conwinder polynomial, a family of multivariable Q orthogonal polynomial, which is regarded as the master class of Macdonald polynomials. First of all, I briefly explain what's the Skewson polynomial and the conwinder polynomial. Next, I will introduce some remarkable property of conwinder polynomials. Finally, I will explain to our research on conwinder polynomials. The first is a combinatorial explicit formula for the Richardson coefficients of the conwinder polynomial. And the second is a parameter specialization of the conwinder polynomial. The second result is a joint work with my advisor, Yanagida Sensei. Let's start with the one variable case. That is the Askew-Wilson polynomials. We will review some symbol related to the Q hypergeometric series. Q is the shift parameter, absolute value less than 1. For non-negative integer k and complex parameter a1.am. We define Q shifted factorial by this. The product of Q shifted factorial denoted by the symbol. The symbol denoted by the symbol denotes the Q hypergeometric series by taking the limit Q to 1. Then we have S plus H phi by ordinary hypergeometric series to phi S. The Askew-Wilson polynomial are family of Q hypergeometric polynomial defined this form with 5 parameters Q, A, B, C, D. Although it appears to be infinite sum, this is a finite sum because here we have the term Q to the power minus L. 3 small examples of Askew-Wilson polynomial are listed below. Constant is very, very complicated. Next, we introduce 2 important properties about the Askew-Wilson polynomial. One is satisfies the 3-term recurrence relation. We define tilde p like this. Then tilde p satisfies this 3-term recurrence relation where L is relation. L is non-negative integer. L is and p minus 1 is 0. The other one is orthogonality. For generic parameter A, B, C, D. So Askew-Wilson polynomial are orthogonal with respect to the weight function W. We note that it is very important to determine the weight function when considering the orthogonality of special function. There are several other hypergeometric polynomials that satisfy the above property besides the Askew-Wilson polynomial. Next, most of them are obtained by specialization, the parameter of the Askew-Wilson polynomial. This is a Q analog of the ASCII scheme from Yanagida sensei's talk yesterday. That is the scheme of Q hypergeometric polynomial obtained by specialization, the Askew-Wilson parameter A, B, C, D. In particular, Lagrange-Bessel and Hermite polynomial are often used in mathematical physics, so you may be familiar with them. The multivariate version of the Askew-Wilson polynomial, which is part of the master class of Q hypergeometric orthogonal polynomial, is actually the Cowinder polynomial that is the main actor of this talk. Next, let X denote n variables and n A denote the Laurent polynomial ring of X. A finite while group of type Cn act on A by permutation. The four element of finite group by permutation of subscript and xj change xj and j minus 1. The subalgebra AW formed by Laurent polynomial, which is the invariant under its action, is written AW. Z to denote the weight lattice of type Cn, and Z plus to denote a set of dominance weights. A dominance weight corresponding to integer partition. And Cowinder polynomial was introduced by Cowinder in 1992 as a multivariable version of the ASCII-Wilson polynomial. If n equal 1, it coincides with the ASCII-Wilson polynomial. Coinder polynomial has 6 parameters, Q, T, A, B, C, D. Note that it has one more parameter than ASCII-Wilson polynomial. In Yanagida Sensei's talk yesterday, he explained the McDonald polynomial as a family of multivariable Q-orthogonal polynomial associated to the affine root system. The Coinder polynomial can be regarded as McDonald polynomial associated to the affine root system of type C check Cn. This has been shown by the works of Nomi, Sahi, Stockman, and Stockman. You may not be familiar with affine root system of type C check Cn, so I will explain it briefly. Here is a summary of notation for root system of type Cn. The weight lattice of type Cn extended one-dimensionally by what is called the null root is written as Hz tilde. The set S is called the affine root system of type C check Cn. So, and linking diagram is like this. We define the extended affine wide group W by the semi-direct product of the Cn type and finite wide group W, and the translation part associated to weight lattice. W act on S. There are 5 orbits due to its action. Each of these orbits corresponding to the parameter T, A, B, C, D. If n equals 1, S has 4 orbits corresponding to ASCII-Wilson parameter A, B, C, D. 4 orbits A, B, C, D. Here basic property of the Coinder polynomial. Coinder polynomial is a C basis for invariant ring AW. Coinder polynomial has the following triangularity by semi-order on the set dominance weight Hz plus called the dominance order. Here M lambda is orbit sum. And the dominance order is like this. Coinder polynomial have 2 characterizations. One is triangular property and Q difference equation. Another characterization is triangularity property and orthogonality. Next, we will explain the Q difference equation satisfied by Coinder polynomial. For each partition lambda, the Coinder polynomial P lambda satisfies the following equation, where D is McDonald-Coinder Q difference operator. Note that D preserves the action on the invariant ring AW. The Coinder polynomial is eigenfunction of D. If n equals 1, this Q if n equal 1, this Q difference equation is the three-term recurrence relation of Askew-Wilson polynomial mentioned at the beginning of this talk. Next, we explain the orthogonality of the combined polynomial. We will impose these conditions on the parameter. The Hermite inner product over the invariant ring AW is determined in this way, where the weight function W of this integral is such that for the inner product, combined polynomial is an orthogonal basis of invariant ring AW. Note that the weight function contains parameter for the combined polynomial. If n equals 1, it is nothing but the inner product of Askew-Wilson polynomial. I would like to conclude by presenting our result on the combined polynomial. First, we will talk about the Littlewood-Richardson coefficient of the combined polynomial. The product of two combined polynomials, P lambda and P mu, belong to the invariant ring AW, which can be expanded by the basis combined polynomial. The coefficients C lambda mu are called the Littlewood-Richardson coefficients for combined polynomial. I have obtained the results. The Littlewood-Richardson coefficients of the combined polynomial are described by combinatorial object called colored alcove walk. Due to time consideration, we omit detailed explanation. If you are interested, please take a look. So, and finally, I would like to present the result of a joint work my advisor Yanagida Sensei. Let me change the parameter to T's and U like this. This is a new parameter corresponding to the 5 orbit of W. Now specializing the new parameter by the way shown in this table. We can recover Macdonald polynomial associated to subsystem of the affine root system of type C check Cn. As a corollary, we can derive various results on Macdonald polynomial of type BCD from property of the master combined polynomial. So, for example, we can recover Ramoy formula of type BC and D from that of C check Cn. Here, Ramoy formula is an explicit formula of Macdonald polynomial in terms of alcove walk. Thank you for your attention.
Okay, thank you. Any questions or comments? Okay. If no, let's thank our speaker again.
Sorry, I have one question.
Okay.
Could you explain what is the relationship with some application to physics?
So, sorry, I don't know, but I don't know, but Ragel Bessel. Sorry, I don't know.
This scheme somehow related to so many kind of hypergeometric functions.
Yeah.
So then, could you explain what is your today's talk object, your main focus in this talk among this ASCII scheme?
Yes.
Which one? This guy, ASCII Wilson.
ASCII polynomial. Yeah.
And this one is a very large class to generate so many kind of polynomials.
Yeah.
Okay. Any other questions or comments? If no, let's thank our speaker again.
Thank you.
And we start the next talk at 10:50.
So maybe it is better to start screen share by next speaker. So next speaker, please share screen and please stop previous screen share. Why?
Yamaguchi-san, please kill the iPad.
Okay. That's nice. So the next speaker can start the screen share. Because it is better to avoid that kind of trouble. So in order to avoid the trouble, it is better to share early. Okay. Thank you very much. This is modular. Modular.
Yes. Modular space.
Okay, so the last talk of this morning's session will be given by Yuya Takahashi from Nagoya University. And the title of his talk is The Modular Space of Spatial Polygons and Geometric Quantization.
Thank you for giving me the opportunity to talk here. I'm Yuya Takahashi, Nagoya University. Now let me begin. First, let M omega a compact symplectic manifold, and let L be a prequantum line bundle over M omega. Here, prequantum line bundle is a complex line bundle over M such that the first chunk class is given by the cohomology class of omega. In addition, we consider the following two structures. The first structure is a compatible complex structure of M omega. In other words, a Kähler structure. Then we can consider the number alpha. That is the dimension of the space of homomorphic sections of L. The second structure is an integrable system F. Then we can consider the number beta. That is the number of lattice points in the image of F. These two numbers seem unrelated, but they are known to coincide in several cases, including toric manifolds, complex Flach manifolds, and the modular space of spatial SU2 bundles on Riemann surface. In this talk, we focus on alpha equal beta in the case of the modular space of spatial polygon. First, we will explain the definition of modular space of spatial polygons. Let n be an integer greater than 4, and let R be an n-tuple of positive real numbers. And let S2Ri be the sphere of radius Ri in R3. Then the modular space of spatial n-gon with edge length R is the following quotient space. By definition, each element of this space is a spatial polygon like this. Hereafter, we assume two conditions on edge length R. The first condition is this sum isn't equal to 0. Under this condition, the modular space is a Kähler manifold of dimension n-3. The second condition is all edge lengths are integers. Then we can construct a prequantum line bundle LR over the modular space. On the other hand, there exists an integrable system on the moduli space called the bending system, which was introduced by Kapovich and Milson. The bending system is a map pi RT from moduli space to Rn-3 associated to a triangulation T of n-gon. For example, when triangulation T is of this type, called the caterpillar, then the bending system is the following map. In general, the bending system is the maps give lengths of n-3 diagonals determined by T, triangulation T. In this way, the moduli space of special polygons MR has a scalar structure and an integrable system. So we can consider alpha equal beta for the moduli space MR. Alpha equal beta on MR was first obtained by Kamiyama. His theorem is the following. If n is odd and all edge lengths are 1 and the triangulation T is the caterpillar, then alpha equal beta holds. That is the dimension of the space of holomorphic section of LR coincide with the number of lattice points associated to the bending system. In this talk, we generalize this Kamiyama's theorem for all n, all r, all t by using the notion of operats. Here is the main theorem. In case of the moduli space of special polygons, we can describe recurrence structures of alpha and beta as morphisms of operats, Fk and Fd. Moreover, we have the following commutative diagram. Here, 3 operats, Carola, W, lib3, and morphism Conto will be explained in the next section. As a corollary of this theorem, we can prove the generalization of Kamiyama's theorem. That is the introduction. Next, we will explain what is an operat. An operat is a sequence of sets together with maps called operatic composition. These data must satisfy the associativity and unit action. Let me skip the detail of this action. We will explain 3 operats in the main theorem. The first is Carola. Carola is a sequence of sets of a rooted plane tree which has no internal edge, like this. The operatic composition is this trivial operation. This is Carola operat. The second is lib3. Lib3 is a sequence of sets of trivalent rooted plane trees, like this. The operatic composition is the grafting operation, like this. This is Lib3 operand. The third operand is W. W is a sequence of sets of these some integer valued function on this product space. Let me skip the detail of W. Next, we will explain morphisms of operands. A morphism between two operands O and P is a sequence F of maps like this, such that these maps preserve operatic composition and preserve unit elements. This is the definition of morphism of operands. Now we explain cont in the main theorem. Cont is a sequence of maps like this, defined by the contraction of internal edges of trees like this. Then cont is a morphism from Lib3 to Corolla. That are operands in the main theorem. Next, we will see the first part of main theorem. That is the construction of morphisms Fk and Fd. Recall that R is H length and T is a triangulation of n-gons. And the moduli space of special polygons is the following quotient space. And LR is the prequantum line boundary over the moduli space. And pi RT is the bending system. First, we will see the construction of Fk. Let VRI be the irreducible complex representation of SO3 of dimension 2Ri plus 1. Then it is known that the number alpha can be described as this multiplicity of SO3 representation. This is the multiplicity of VR1 in this tensor representation. Based on this fact, we define Fk as follows. For each Corolla, we define this integer valued function in this way by using multiplicity. Then we can show that Fk becomes a morphism from Corolla to W. Next, we will see the construction of Fd. As shown in this figure, trivalent rigid plane tree is the dual graph of a triangulation of n-gon. Then, by identifying triangulations with trivalent rigid plane trees, we can show the following proposition. The number beta, that is the number of lattice points associated to the bending system, can be described as the number of some integer edge labyrinths of tree T. Based on this proposition, we define Fk, Fd, as follows. For each T, we define this integer valued function in this way, using the number of some integer edge labyrinths of T. Then we can show that Fd is a morphism from lib tree to W. That is an overview of the first part of the main theorem. In the last section, we will see the second part of the main theorem. The second part of main theorem is this diagram commutes. The key here is the following lemma. Let O be an operand, and let F and G be morphisms of operand from lib tree to O. If F1 and Fg, F2 and G2 are equal, then F and G also equal. What's important here is that F and G are morphisms of operands, because these morphisms of operands play a role of a recurrence relation in some sense. So this initial value agreement implies the agreement everywhere else. Now we apply this lemma to the case where these composition morphisms and Fd. Note that the first condition automatically holds. So what we need to check is the second condition, that is this equality. Let's see the proof briefly. The key to prove is the Krebs-Gordon rules on SO3. Note that the set lib tree 2 is the singleton like this. By definition, Fk and cont, this value is this multiplicity. The multiplicity is by the Krebs-Gordon rules on SO3. This multiplicity is 1 if D C1, C2 satisfies the triangle inequality, and 0 otherwise. the last equal is easy to check by the definition of FD. So we obtain the equality. Now, by applying the key lemma, we obtain the commutative diagram. Finally, we deduce the generalization of Kamiyama's theorem from our main theorem. The left-hand side has been described by Fk like this. On the other hand, the left-hand side has been described by Fd like this. By main theorem, these two morphisms of operands coincide. So the both sides are equal. In this way, we prove the generalization of Kamiyama's theorem. That's all I have to say. Thank you for your attention. Thank you.
Can I have a question? Sorry, can I have a question?
Yeah, go ahead.
Oh, sorry. Okay. Sorry. My video has something wrong, and I will try to fix it in the afternoon. And I have a question that does every ON for O equals to your corolla is a singleton?
Sorry, one more, please.
Okay. So I wonder, you define an upright corolla, right?
Corolla is this operand.
Yeah. So does it mean your corolla n is a singleton for each n?
Each n. Yes. Each n. Yes. For each n. N is the number of leaves of corolla.
Okay. Okay. So your corolla n is just a singleton, and I'm not quite sure about why such an upright is every nth set is a singleton that can sorry, let me reformulate. Why a morphism from such an upright can encode such information. Maybe I don't get your morphism from corolla very clearly.
Why corolla emerge? Your question is?
So a morphism of between operands is a sequence of maps. Right?
Yes, yes.
And corolla n is a singleton, right?
Yes.
So a sequence, so a morphism from corolla is just a sequence of maps from singleton. Can I say that?
Yes.
Yeah, maybe I'm confused somewhere.
Corolla. FK is the reason FK become more, why FK is a morphism? Your question?
FK is a morphism from Corolla to W.
Yes.
Right?
Yes.
And this morphism, does this morphism consist of a set FK for each n? Right.
Sorry, sorry, one more, please.
Okay, so does FK consist of FKn for each n?
Sorry,
Okay.
Mike is
Okay. Is there something wrong? Okay. Shall I repeat myself?
Yes.
Okay. Thank you. My internet may be not well. So my question is that so if Corolla is n, my first question is that is Corolla n a singleton, and my second question is that if Corolla n is a singleton for each n, then the data of FKn is a map from a singleton set. So the data of FKn is equivalent to choose an element in Wn. Am I right?
Yes.
Okay. What do you choose in Wn for FKn?
W is an operator of integer valued function.
Oh, okay.
So this
Okay.
is W.
Okay. Thank you. Thank you. Thank you.
Okay. Any more questions or comments?
Sorry, I have one question. I could not understand the detail. So, firstly, you consider SO3 group. Why you consider that group?
SO3 group is the definition of the modular space of special polygons is the quotient by SO3. So SO3 SO3 image.
Quotient SO3. You consider S2 R1 Rn. What is S2 R1? Sphere with radius.
Yes.
And you have that condition U1 plus UN equal to 0.
Yes. This condition is this vector is closed. This vector, sum of this vector is 0.
Okay, I understand. So, but still, no. I'm slightly confused. Your definition is U are vector.
Yes. You are vector.
Equal to U mu inverse 0. What do you mean mu 0?
Sorry. Mu is this this product space is a symplectic manifold with SO3 Hamiltonian action. Mu is the momentum mapping.
Momentum mapping. R3 element to R3.
Mu is this map.
This one?
Mu is this map.
This sum, okay. This sum,
yes.
Okay, I understand. This sum, okay. Mu is this sum. Why you consider that object? Why you consider that object?
I consider the object First, I want to generalize the Kamiyama's theorem like this. So we deal with the modular space of special polygons.
No. I'm asking the importance of that object, mathematical or physically. So, why this object is so interesting?
So, my operatic approach is isn't know so this operatic approach seems new approach because the proof of Kamiyama's theorem is Kamiyama proved this theorem by using the recurrence relation of the beta.
So maybe the reason why you consider this one is that one is open problem.
Open problem.
At least this generalization is unsolved. So then you consider that problem.
Yes, and generalization is solved. But by my operatic approach, the generalization proved.
Okay, I understand this.
So,
Can I have another question? Sorry.
Yeah, please go ahead.
Thank you. So I'm not familiar with Keller manifold or your topic, but I'm very curious. Can I ask you that you have mentioned that there are different contexts. There is a phenomenon of alpha equals to beta, right?
yes.
So do they can also be proved by an opera approach?
Opera.
Yeah, here.
We I want そうですね。I prepare てか I そうSo sorry, one more please.
Yeah. So you have told us that there is alpha equals to beta in these three cases.
Yes.
So can I have some idea of that, whether these three cases or some of them can be proved by operatic approach, like the one you use?
The modular space of flat SU bundle of Riemann surface. This case, the operator approach. We can do operatic approach in this case. I prepare the paper about this in operatic approach now.
Pardon. Okay. I did not hear well. Sorry.
The modular space of flat SU2 bundle of Riemann surface, we can apply this operatic approach.
Okay, thank you. Okay, thank you very much.
Thank you.
Okay. Any more questions or comments? Okay, if no, let's thank our speaker again. And the afternoon session starts from 1:30 p.m.
Oh, thank you very much.